Hello there. Welcome and thank you for joining us today. This session is all about a practical challenge that's becoming increasingly critical as satellite communications evolve. How do we realistically emulate satellite radio channels for development, integration, and testing, especially when working with modern 5G or software-defined systems? My name is Arpad. I'm part of Lasting Software, a company set on building advanced solutions and tools that bridge the gap between end-to-end theory and implementation, between radio channel theory and real-world signal testing. And today, we're proud to introduce to you CELEOS, our SDR-based satellite channel emulator. So without any further ado, let's dive right in. Did you know that most satellite channel emulators weren't built with the 5G NTN in mind? And relying on them could derail months of development. Even as hardware-based emulators have evolved to acknowledge 5G, many of them still follow a legacy mindset, focusing on fixed configurations, rigid signal paths, and limited scalability. While some have introduced 5G updates, they've largely maintained the traditional approach, hardware-centric, difficult to reconfigure, and tightly coupled to predefined use cases. This makes it hard to support the flexibility and agility required in modern NTN workflows, especially for rapidly moving LEO satellites, software-defined payloads, or SDM-based testbeds. Yet satellite communications have never been more vital. What would the motivation be for such a product? Satellite communications play a crucial role in the global communication system. Since the launch of the first artificial satellite in 1957, over 20,000 satellites have been launched into orbit, and more than 11,000 of them are still operational today. In recent years, satellites play a new role. By integrating satellite communications with terrestrial ones in 5G NTN introduced in 5G release 17 and 18, this has become quite crucial. Reflecting on the major role of satellites in telecommunications and on the high price of the satellite and launch operations, it becomes obvious the need to test the communication system before the launch in conditions as close as possible to the real ones. A satellite radio channel emulator plays a vital role in the development, testing, and optimization of satellite communication systems, replicating the characteristics of the satellite radio channel and allowing engineers to assess how a satellite communication system will perform in real-world conditions without cost and time-consuming field tests. Satellite radio signals are subject to various impairments and distortions as they travel through the Earth's atmosphere, including delay, Doppler effect, multipath fading, signal attenuation interference, and other channel effects. The channel emulator mimics these conditions to simulate the behavior of a satellite communication link accurately. Let's start at the beginning. Satellite radio signals are subject to various effects and impairments as they travel the high distance between satellite and ground station. Therefore, the impairments such as delay, path loss, shadow fading, noise, Doppler shift, power amplifier non-linearity are important ones to take into account when developing an accurate channel emulator. So let's jump right into them. The delay. The large physical distance between a satellite and the ground station introduces a significant propagation delay in the satellite communication, especially when compared to terrestrial systems. Therefore, slant range, or the line of sight distance between satellite and ground, varies by satellite orbit. For geosatellites, the slant range is approximately 36,000 kilometers, resulting in a one-way delay of about 120 milliseconds. For LEO satellites, the slant range is typically around 500 to 2,000 kilometers, leading to one-way delays between 1.66 milliseconds and 7 milliseconds. In the case of geosatellites, the satellite remains in a fixed position relative to the Earth's surface, so delay can be treated as constant. In contrast, for LEO or MEO satellites, the delay is time-varying due to the satellite's movement relative to the observer on the ground. This dynamic behavior makes it important to consider both the absolute delay and the rate of change of the delay, known as delay rate. In practical systems, especially those involving beam tracking, synchronization, HRQ timing, or buffer management, this changing delay or delay rate becomes a critical impairment to model and test against. In CELEOS, this variation is emulated in real time, allowing system developers to validate timing resilience under realistic, fast-changing link conditions. This figure here shows the absolute delay and the delay change rate as function of the times for the LEO satellite Starlink 1011 for Starlink constellation. The path loss. According to 3GPP study, on the new radio to NTN networks, the signal attenuation between satellite and ground terminal includes several components that determine the signal path loss as follows. The total path loss can be expressed as the sum of the basic path loss, the attenuation due to atmospheric gases, the attenuation due to ionospheric and tropospheric scintillation, and the building penetration loss, all expressed in dB. Basic path loss attenuation, or PLB, has three cumulative components: free space path loss, shadow fading, and clutter loss. Going further, the free space path loss, or FSPL, follows the free space propagation model and depends on the distance d in meters and carrier frequency Fc in gigahertz according to the following equation. Shadow fading, or SF, is a random value following a normal distribution with zero mean and variance as per 3GPP TR 38811 V1510, namely the study on new radio to support NTN networks. You might also be asking about clutter loss. Well, clutter loss value depends on the propagation scenario, satellite elevation, frequency band. Henceforth, only line-of-sight conditions are considered, and clutter loss can be ignored. Attenuation due to absorption in atmospheric gases depends mainly on frequency, elevation angle, altitude above sea level, and water vapor density, and can be neglected at frequencies below 10 gigahertz. However, for low elevation angles, the slant range has a significant part in atmosphere, and attenuation by atmospheric gases can then be significantly important for frequencies above 1 gigahertz. The Doppler shift. The time the satellite completes their orbit depends on satellite type, with different speeds up to 28k kilometers per hour for LEO orbit. Due to satellite movement with relative high tangential speed with respect to ground station, the carrier signal experiences a Doppler shift that can be, in some situations, very large compared to terrestrial communications where low speed compared to satellites are involved. Also, the relative speed between the satellite and ground station varies in time. This figure here plots the Doppler shift and Doppler rate for the LEO satellite Starlink 1011 for a carrier frequency of 5 gigahertz. Maximum Doppler shift and Doppler rate is achieved for LEO satellite at high carrier frequency. Power amplifier nonlinearity. By nature, the satellite suffers high constraints in all carried equipment, including onboard power amplifiers. Hence, they are expected to operate near to maximum rated output power, close to saturation. As power amplifiers are highly nonlinear in nature, this regime causes generation of unwanted signals like intermodulation distortion and intercarrier interference. PA nonlinearity for traveling wave tube amplifiers and solid-state power amplifiers have been implemented in accordance with the amplitude modulation to amplitude modulation and amplitude modulation to phase modulation characteristics in the PA.